you all for being here. So the title of my presentation is a little bit large. So the real title would be optimal control of sleep mode schemes in mobile networks. But I did not want to bother Dario by changing title, so I kept this. So it's a little bit a little introduction of this talk. So since 2007, operators have been engaged to reduce their energy consumption. For example, Orange Group wants to reduce its energy consumption by 15% in 2020 compared to 2006 levels, and the CO2 footprint by 20%. So why CO2 footprint? We aim to reduce it by more by 20%, while energy consumption by 15% only. That's because we want to use also renewable energy and nuclear energy. So we say that 15% in energy consumption would be equivalent to 20% in CO2 footprint. So there are two main difficulties with this. That the first one is that we don't know exactly what were the levels in 2006, because we don't have monitoring tools. We start deploying monitoring tools on our networks, so it's very difficult to say we have reduced by 10% or 15%. And the second is that in 2010, 2011, we started to deploy 4G networks. So we have to reduce the energy consumption where we deploy more sites, and we also plan to keep our GSM networks. So it will be very difficult to reduce the energy consumption while keeping all the base stations and adding more base stations. I focus here on the mobile network energy consumption because I work on mobile networks, and because they consume 21% of the overall energy consumption of the network. So making mobile access networks green is essential. So if we focus now on the energy consumption of mobile access of mobile networks in general, we can say that all the components of mobile network have a small portion of the energy consumption, except the base stations. So these figures are a little bit old, 2008 I think, but they are still okay now. So we see that the energy consumption of mobile phones is low. We have 3 billion subscribers, but they account for only 2 terawatt hour. These are global figures, and the energy consumption of base stations is very large. 80% of the overall energy consumption of mobile networks. So we focus on reducing the energy consumption of these base stations. So there have been several projects that were launched in order to work on making mobile access networks green. There are some European Celtic projects, so OperaNet and the following one, OperaNet 2. There was the famous project Earth. It was the FP7 project, and there's a global consortium, Green Touch. So now OperaNet 2 and Green Touch are still ongoing, and I'm active in both. So some examples of green base stations. So you can see here that we can deploy base stations like a tree, and if you look, you can see that there are 3 antennas here. Another example of green base station, it depends on the place. So here it's in Morocco, here it's in Finland, and here it's in France. So it's only a joke. It's not really like that. So these base stations are green, but they are not necessarily energy efficient. They may be energy efficient or no. We want to focus more on the energy consumption of this of the base stations. So if we take an example of one site that has 3 sectors, each sector has 2 carriers. For example, 2 3G carriers, each one of 5 megahertz. A typical configuration would be that you have the main AC input, you have the rectifier that transforms AC to DC, you have digital signal processing that is common to the site, and then you have for each sector its own PAs. So each power amplifier can serve 1 or 2 or 3 carriers. Here I give an example where each power amplifier serves only one carrier. So you have 6 power amplifiers in this site, and 80% of the overall power consumption of the base station is the consumption of the power amplifier. So and we also observe that even when traffic is very low, power amplifiers consume a lot, because we have to these power amplifiers are still active because we have to transmit channels for pilots, for example. So if in this figure here, I try to put an example of consumption of sites. Traffic changes with time. So in blue, there is the offered load, the load of the base station. It varies between 0 and 50%, while the energy consumption of the site is always around 60% of this maximum power. So the energy consumption does not change a lot. So the only way to reduce the energy consumption of base stations is to switch off completely some PAs. So the sleep mode, the principle is very simple. It's applied in all electronic devices. When a device is not active, we switch it off. So it seems simple, but in reality, it's not very simple. So I'll talk a little bit about sleep mode of macro base stations, and then I'll talk about sleep mode for small cells and some activities in standards that deal with these aspects of green. So I take here the same example as before. So we have a site with several cells. So one cell is maybe a carrier for 3G, maybe a MIMO transmitting chain in LTE. So the energy consumption model, the power consumption model is generally like that. You have a constant power that is due to rectifiers and signal processing, and for each sector you have a number of PAs. So each PA will consume a constant power, and then a power that depends on load. So if rho is load of power amplifier number R, there is a part that is independent of load in the power consumption. You have for the PA a part that is independent on load, and another part that depends on load. So C is the efficiency of the power amplifier. For example, it's around 20%. So if this power amplifier produces enough power of 20 watts, the real consumed power would be 20 watts divided by 0.2. So if we put a PA in sleep mode, for example, we put some carrier in sleep mode, all the part of the power consumption, the fixed part and the variable part will go and will disappear. So an illustration of this is that if you can apply this in 2 different moods. You can say I will apply a sleep mode in a static way. So I will monitor the overall traffic, and then when traffic is low, I will put some power amplifiers in sleep mode. And you can make this in a more dynamic way. So on a time scale of few seconds, you choose how many power amplifiers you will put in sleep mode, and then you will adapt it with time. So this is an example of HSPA traffic on one site, and then you can see that in here I put the power consumption. So you can see that during night traffic is very low, but energy consumption remains high. And if you apply semi-sleep mode only at night, because in practice the first scheme is only at night, you will have a large gain in energy consumption at night, and then the energy consumption will stay constant. But if you apply it on a few milliseconds, on a few second scale, you'll gain more, even at high traffic. But the issue with that is that it's complex to implement. You need intelligent controllers that monitor traffic each few seconds, and then take a decision to activate or not a PA. So we work on implementing some optimal controllers for sleep modes in base stations using control theory. I give here an example. So what is difficult in mobile networks is that you don't know the capacity of a cell in advance, because you have different radio conditions. If you are at cell edge, you will have a low throughput. If you are at cell center, you have a large throughput. So the controllers have to take into account not only the number of users in the cell, but also the distribution of this number of these users among the different radio conditions in the cell. So if I give a simple example where you have cell edge users and cell center user, we make use of Markov decision processes, MDP, in order to derive the optimal policy that associates to each distribution of users a number of carriers that are active. So these MDPs need some utility function or reward function. This is the amount of gain in energy, but the cost will be degradation in quality of service, because if you have data calls, you have two carriers. They can use both carriers. They will have a larger throughput. But if you activate only one, they will have the throughput divided by 2. So we illustrate the optimal policy that we obtain using MDP. So we see that we have several observations. So here, this is the number of active users, and then the optimal controller will choose what is the threshold for passing from one carrier to 2. What is the threshold for passing from 2 carriers to 3, and what is the threshold for passing from 3 carriers to 4. So the first observation is that the optimal policy, as we illustrate here, does not depend on the distribution of users on the different radio conditions. It depends only on the number of users in the cell. So it's not. So the policy will change a little bit with this distribution, but in general, if we take it depending only on the overall number of users, we will not lose very much accuracy. And then the second observation is that the optimal policy depends on the volume of traffic. So the optimal policy at night is different from the optimal policy during the day. So it's logical that if you have an overall traffic volume that is large, it's the optimal policy would be to pass to switch on carriers early. While if the average traffic volume is is low, we will wait more before activating a carrier. So what is the issue with this? We have some implementation issues because we have observed that this optimal policy depends on traffic, but it also depends on the capacity of cells. So it will be very difficult to apply MDP theory offline and then find the optimal policy and apply it to base stations. We need to implement some online controllers, and we know that implementing MDPs online is not easy. So I illustrate here how this optimal policy depends on the capacity of the cell. So we can see that if the cell capacity is large, the optimal policy is different from the case where cell capacity is low. And in practice, we don't know exactly what is the cell capacity. It depends on interference. It depends on the position of users. If all users are near to cell edge, if you have a hotspot at cell edge, the capacity of the cell will be lower than a cell where we have a hotspot near the base station. And we tried to apply this on a real network. So we took a part of Paris network and we applied the MVP controllers by simulation, and we have seen that so these sites have only two carriers. So even with only two carriers, we have different thresholds that depend on the base station. So if we want to have a non-line policy, we have to implement some learning algorithms in base station. So we have chosen to implement the multi-arm bandit algorithm. We also tried Q learning, but multi-arm bandit is very powerful in this case. So the idea is to exploit the history. So observe what happened in the history, and then explore some new possibilities in order to find the optimal policy. So we found that controllers were very quickly converging to the optimal policy. And here it's an example of traffic of some base station. We can see, and this is the results after applying the online controller on the base station. We can see that the quality of service remains acceptable. Here it's 80%. It's acceptable because it's not blocking. Here we said that we want that users have more than 5 megabits per second. So if 80% of users have more than 5 megabits per second, we consider that quality of service is okay, and energy is a little bit increasing when traffic increases. And overall, we have observed around 25% of energy saving during the day. So I will not move to the second part, that is how to apply this principle of sleep mode on heterogeneous networks that are composed of both macro cells and small cells. Because you all know that in LTE Advanced, we will keep the macro base stations of the 4G macro base stations, but we will add to them some small cells. We already began to deploy some micro and pico cells and femtos, but it's expected that we will deploy massively a large number of small cells. These small cells can be installed by the operator itself, like pico cells outdoors or indoors. Or these small cells can be installed by users within their homes. So the idea is that small cells will increase the spatial reuse of the spectrum, and then they can offload traffic of macro base stations, but they will consume energy. So the same principle as before. If we want to have energy efficient small cells, we have to be able to put them in sleep mode. So I illustrate here an example. So what is easy? So here we have an example with three macro base stations and three small base stations. What will be easy is to put a small cell in sleep mode, because when a small cell observes that there is no traffic in its coverage, it can go in sleep mode. But what will be difficult is to put them again active, because when a small cell is in sleep mode, it does not send any pilot channels, so so it will not know. Users will not know that the small cell exists, and the small cell will not know that users arrived in its coverage. So the optimal controllers need to be able to awaken some small cells when traffic arrives. So we begin by a very simple case. So we have always in LTE what we call the X2 interface. So it's a backhaul link between neighboring sites. So this includes small cells. Picocells may be linked via a fiber to the macro cell, and femtos will be linked, but via DSL. So it will be for femtos a logical link, while for Pico it will be a physical link. So we begin by the case where there is a completed traffic information. So if you have GPS in mobiles, it will be easy to implement sleep mode. But in practice, you don't have GPS in mobile, so you can make errors. So I begin by illustrating the case where GPS exists for all mobiles. We can use the MDP theory as before. So the state of the system is the number of users in the macro base station and in the small base station, and then each action would be to switch on or switch off some small base station based on the number of users in the cell. And here you have complete information, so you can use normal MDPs. So for illustrating this, so here I put for different number of users in the macro cell, I illustrate the optimal policy, where is the how to switch on or off the femtos. So in this region, both femtos are off, and in this region, one of the two femtos is off. And in this region, when traffic is high everywhere, both femtos are on. So it's very easy to apply this, and we can observe that it's almost a threshold policy. So you can put a threshold on the number of users in the femto base station, and then it may happen that you have some errors, but if you put a threshold here, you can decide to put the femto on or off, depending only on its own number of users. Now we move to a case that is more difficult, where you have only partial information about where users are. So for example, if you use some localization methods, so you don't know exactly where users are, but you have a guess. So here it's not a normal MDP, because you have a real estate that is number of users in each base station, but you have also an observed state where you know only the number of users in the small cell that is active, and you know the number of users in macro cell plus small cell 2 plus small cell 3, and you have to guess where are users based on some partial information. So you have to construct some belief about the real hidden state, knowing the observed state. So this corresponds to partially observable MDP that can be also solved. So we implemented this and solved it. And here I illustrate some results that we obtain. So when traffic increases, we put the quality of service. So how many users have more than a target throughput, and the energy consumption. So we can see that in the case where all femtos are active, so you don't implement sleep mode, energy consumption is high, but also quality of service is high. When you implement the sleep mode with complete information, this one you will gain in energy consumption, but you will lose a little bit in quality of service. And when you introduce partial information, your gain in energy consumption using POMDP will be close to the case where you have complete information. But if you don't have any information about where users are, so you will make many errors, and then the energy consumption gains will be low. The last case here is when you have delayed information. This means that you can obtain information about where users are, but you have to wait some times. For example, if you apply some algorithm where base stations will have some cooperation among them to localize users, the information about where users are may arrive, but after some delay. So here you have also the hidden state and the observed state, but after some time you will so at each time you will observe this state, but after some time you will be able to know exactly the state of the system. So this can be modeled as a delayed MDP. Normally, delayed MDP, it's you use them when you take an action, and then you will wait some time before the result of this action will be effective. But here it's the inverse is that you don't know what is the state, so you have to delay your action. But formally, you can use the same methods to both cases. So we applied this, and here we can see that if you have delayed information, it will not be very helpful when the delay is large. So if you want 95% of quality of service of users, you can support only half a second of delay, and afterwards it will correspond as if you are not able to make a sleep mode. So delayed information is very annoying when you want to implement a sleep mode. For ending my talk about this, I will talk about some activities in standards about energy efficiency. So if you want to implement some sleep mode algorithms in base stations, you don't need to put them in standards, because each vendor will implement its own schemes. So what you can put in standards are only how to assess that a base station is green. So what are the methods that you can use to certify that a base station is green? So we do this in ETSI. And second, you will put in standards what are the interfaces between base stations that you need in order to be able to implement some schemes for a sleep mode. So first, in ETSI, we began, I think, in 2010 to standardize very simple schemes where you want to put a base station in lab and to measure its energy energy consumption before activating energy-saving features and after activating them. So if you want to test sleep mode, you have to have some traffic that will change in time. So in labs, we put the base station, and we put some controller that will control that will implement the sleep mode algorithms in the base station, and then in each of the sectors we'll put a number of users that go between on and off states in traffic, and then we assess the energy consumption and the energy efficiency. So it's not very realistic, because the traffic environment in real networks will be changing faster than this, but it's a way to assess if the sleep mode algorithms of vendors are good. So this is a standard that has been delivered in July 2013, and we are working on the next version that will be by the end of this year. And we have the objective of this is to be able to compare base stations from the energy efficiency point of view, and to test the energy efficiency features like sleep mode in lab. We are also working on a standard, an ETSI standard, to assess the energy efficiency of a whole network and not of a single base station in lab. So this corresponds to select some base stations from the active network, use some monitoring tools to monitor their energy consumption and their traffic, and then use some statistical methods in order to compute the energy efficiency of these base stations and extrapolate them to cover the energy efficiency of the whole network. So the objective is to compare a network, and when you implement some energy saving features on the network, to compare the energy efficiency before and after. So this is a standard that is ongoing, so we'll finish it also by December of this year. So the last activity in standards, so it's in 3 GPP, because we want to ensure that the sleep mode schemes that are proposed by vendors and by operators can be applied on real networks. So what we want is to put in standard the interfaces that will enable this. So what is possible what is possible now is to exchange some loads information on the X2 interface, and to send commands to activate some base station that is in sleep mode. But what is not possible now in standards is to identify among base stations if the base station can be put in sleep mode without having a hole in coverage. So if you see here, you have an example of a network, and we have identified some base station that can be put in sleep mode without creating holes in coverage, because they are close to other base stations. So for making this, we have used some operational tool where we put base stations, and then we test if we remove this base station, if the coverage will be ensured or not. But what we are doing now in 3GPP Run 4 is that to search for to allow exchanging information between sites that indicate if the coverage of this base station is completely overlapping with the coverage of other base stations. So we are trying to make in standards these interfaces. But what is now in research is how to make some schemes that identify automatically by some exchanges between neighboring base stations if a base station can be put in sleep mode without creating a hole. So it's now in research. We don't have schemes. We will try to apply some learning algorithm between base stations, but this is ongoing work. So I will finish my talk now by some conclusions. So reducing energy consumption of base stations is essential because they consume almost 80% of the energy of the whole mobile networks. And sleep mode is a good way to ensure this. So the principle is to use only the power amplifiers that are needed in order to deliver a good quality of service. So sleep mode can be applied to power amplifiers within one base station and can be applied also to small cells or to whole sites. When you apply sleep mode, you need optimal controllers. So if you want to make this offline, you can use MDP theory. But if you want to make this online, you need to implement some learning algorithms in base stations. And in standards, we are trying to work on two different ways. The first one is how to assess the energy efficiency of base stations and how to test that sleep mode schemes are efficient. And the second one is to allowing some distributed operation of sleep mode of base stations by some exchange of information between sites. Some reference on this. So this is the link of the OperaNet2 web page. There are some papers, some presentations. There are many papers on sleep mode available. I put here only two. And the standards ETSI, so you can find them on the ETSI server. This one is available. This one is not available, but there is a report that we achieved last year that was the base of this one that I think we can share it. Thank you. If you have questions.
Questions?
I have one question regarding the user association after switching off the small cells. I mean, users they go to the macro base station or to other micro base station.
So in the results here, we illustrated only the case where they go to the macro base station because coverage of small base stations are not overlapping. We had only a small number of picocells. But we also studied the case where you have very dense deployment of small cells. In this case, they can go to the macro base station or to the small base station based on the coverage of these small base stations.
Okay. But if you consider, I mean, the energy consumption of micro base station, it's better for user to go to small cells.
If the coverage of small cell is sufficient, if it's covered by two small cells, it will be better. But in general, the coverage is not overlapping between nearby small cells.
Jim? You gave some targets for energy savings at the start of your talk. What would your MDP and other multi-arm bandit results give with respect to that target? Are you on target, or are you wildly less or wildly more?
So the last results we obtained were by putting some whole macro sites in sleep mode. So it was around 18% of saving. So it would be close to the target of 15% of saving, but it's the energy consumption of 4G after sleep mode compared to the energy consumption of 4G before sleep mode. But knowing that in 2006 we did not have 4G, So this energy consumption gain is on something that did not exist before.
Yeah, so the target's a little bit difficult. But is the target for the entire mobile network at the different traffic levels which you will have in 2006 and 2020? Because that changes a lot, doesn't it? The comparison is between carrying all the traffic in 2006 and carrying all the traffic, which is probably 100 times more in 2020.
Yeah. So what we are trying to explain now is that we will reach the targets and even exceed the targets of the energy efficiency. So how many bits you can carry per watt, how many bits per second you can carry per watt. So you will have large gains in this, but you will not be able to reduce the absolute value of the energy consumption. I think that absolute values will increase, but the energy efficiency will also increase.
The target is on the energy efficiency.
The target was on absolute values, but we can argue that traffic has increased 20 times or more.
I have a quick curiosity question. Does anyone look at this aspect in terms of in relation to cloud-based radio access networks? You know what China Mobile is doing, of like just leaving the radios out there and putting everything back into the cloud? Is anyone looking at that?
Yeah, the first studies show that you can gain in energy consumption because of the pooling. So you put many signal processing together, and then you don't have cooling for each site. So you have only one centralized site with cooling. So you will gain with this. Gains are important. But I think that the deployment of Cloud Run will not be based on energy consumption only. It will be based because you will have many costs due to fiber links. So you have to deploy fiber links. The cost, the capex will be very high compared to some gain in OPEX.
Oh, I thought the idea of C-RANs was that you had fiber already to the base stations, and that was.
It's not the case everywhere.
Okay.
As you explained, the issue is that you need to keep transmitting the pilot, right? This
Yeah.
is why you cannot turn off easily a base station. Now, in a given region, usually you have several technologies running at the same time. 3G, the 4G, maybe others. And each of them is transmitting the pilot.
Yeah.
One could imagine that the standards evolve and you have a standardized pilot that everyone is using. And if you coordinate the technologies, then you need to only one of them to transmit the pilot, right?
Yeah.
And to announce that the other exists as well. This, I think, will have a large impact on the power reduction.
So this idea is in Green Touch consortium. It's studied the idea of making common control network, a large control network that indicates, that finds where are users, and then it sends commands to base stations to be awakened. This may be in the 5G, but it will change radically the architecture of the network. So it's a long-term solution. What I explained now is only short to mid-term solutions. In 5G, you have also the massive MIMO solutions where you have hundreds of antennas with very low power consumption per antenna, and then you choose among these antennas which will be used to serve. I think these solutions may reduce, may give very large energy gains, but it will be only in long term on 5G after 2020.
Okay. And what about the directed beams? The fact that you can, nowadays, with some antennas that are in the field, you can direct the power, right?
Yeah, but how to know where is exactly the device if you want to direct the power? So the research studies suppose that you have a very accurate feedback and based on this feedback, you will determine which beam you will use. But in practice, it will be very difficult because beams will be very narrow, and then if you make a small error, you will not reach the user. So I don't know, perhaps with some advances in physical layer communications, it would be possible.
Other questions? Okay, thank you very much.
Thank you.